I'm gonna continue these challenges here from where I stopped. I think I'm gonna put 1 hour here, and then if I feel like it, I'm gonna do more. There's a lot of things that I need to do off stream, so not sure how long I can stay. I can do this. Using an interface. Continue our previous example with number interface. Once we've defined the interface as contract number interface, function getNum address my address public view returns uint, we can use it in a contract as follows. So I think I stopped on the definition things. I don't remember really well. So this was to use the kitty interface in the contract, if I remember. Number interface. Use it. The address of the favorite number contract on Ethereum. Number interface number contract equals number interface address. Now number contracts is pointing to the other contract. So it uses, yeah, I'm not sure if I get it, to be honest. It's using number interface to point this address here to number contract. Yeah, I guess that's what's happening. Now we can call getNum from that contract. GetNum message sender and do something with num here. So number contract dot getNum. It's kind of hard to remember exactly what I was doing in the last couple of challenges. In this way, your contract can interact with any other contract on the Ethereum blockchain as long they expose those functions as public or external. Yeah, that I remember. That to use one contract in another one, you need to specify external in the functions. Put it to the task. Let's set up our contract to read from the CryptoKitties smart contract. So they already give the address here. Initialize here using CK address from above. So I guess I need to do kitty interface. Then I've saved the address of the CryptoKitties contract for you under a variable name CK address. And let's create kitty interface named kitty contract. Contract equals kitty interface CK address. I think that's it. So just pass the address to this function definition. Initialize the scalar, just like we did in number contracts above. Okay. This getKitty function is the first example we've seen that returns multiple values. Let's look at how to handle them. I think I saw a video on this already. You just put it in parentheses, the return values in the order they were specified here. Put it to the task, time to interact with the CryptoKitties contract. Let's make a function that gets the kitty genes from the contract. Make a function called, define function here, function called feed on kitty. There's 0 arguments, then it's probably gonna be public. you take two uint parameters, zombie ID and kitty ID, and should be a public function. So assume I don't have to specify views. Yeah, maybe I do need to put returns actually, because it's probably gonna have multiple values to return. The function should first declare a uint named kitty DNA. Note, in our kitty interface, genius is a uint 256. But if you remember back to lesson 1, uint is an alias of uint 256. They're the same thing. The function should then call the kitty contract dot get kitty. So this one dot get, which I assume is a function of this contract here. Oh, it is the function. The function should then call the kitty contract dot get kitty function with kitty ID and store genes in kitty DNA. Star genes on kitty DNA. What does that? Memory get kitty returns a ton of values. 10 should be exact. Nice, I counted them for you. But all we care about is the last one, genes. Count your commas carefully. Also assume you have to put a bunch of commas. 1, 2, 3, 4, 5, 6. And I have to store this on genes. Finally, the function should call, feed, and multiply, and pass it both kitty DNA and both zombie ID and kitty DNA. Also, I guess I need to put this two in the same line, probably. Yeah. And then I call feed and multiply and pass zombie ID, kitty DNA. That makes more sense to me. So I don't need these returns. Let's check. So let me see how many I did here. I think I did an extra one. Oh, maybe I need to get something else actually. Yeah, I need to erase this. And just put the commas. One, two, three, four. So kitty contract, which is this. Then get kitty, which is this. And I'm returning. Maybe I should put genes there. Or a kitty ID. But I think I did this before. It doesn't work. So here, returns like this. This is how you do multiple assignment. So it's basically destructuring these values here. Or if we only cared about one of the values, so it's on the other side, I think. So I think I'm understanding this the wrong way. I should call the function with this on the other side, but then make a function called FeedOnKitty. The function should first declare a uint named kitty DNA. For kitty, in our kitty interface, genes is a uint. They're the same thing. The function should then call the kitty. Oh, I think I get it now. So I need to put this here. And 1, 2, 3, 4, 5, 6, 7, 9. And then I just call the function like this. Probably. So it doesn't work. Oh, I need to declare first and then put there. Oh, because I'm not calling anything here. No, but I shouldn't be calling. So maybe I need to declare the variable first. Kitty DNA, kitty DNA. Still, oh, I forgot this. It's still not correct. So it can't be that. Let me think. But if you remember back to lesson 1, okay, the function should then call the kitty contract dot kitty get kitty function with kitty ID with kitty ID. So maybe I should be passing this. And star genes in kitty DNA. The kitty returns a ton of variables. Carbal's genes. Counter scarf. Oh, maybe I need to put one more comma. Okay, there we go. I'm confused about how many arguments. Oh, I guess it is here actually. Specifying that you have to put one argument. Our function logic is now complete, but let's add in one bonus feature. Let's make it so zombies made from kitties have some unique feature that shows they're cat zombies. To do this, we can add some special kitty code in the zombies DNA. If you recall from lesson 1, we are currently only using the first 12 digits of our 16-digit DNA to determine the zombie's appearance. So let's use the last second unused digits to handle special characteristics. We'll say that cat zombies have 99 as their last 2 digits of DNA since cats have 9 lives. So in our code we'll say if a zombie comes from a cat, then set the last 2 digits of DNA to 99. If statements in Solidity look just like JavaScript. Put it to the task. Let's implement cat genes in our zombie code. So I need to modify the function definition. Let's change the function definition for feed and multiply so it takes 3 third argument. String memory species Next, after you calculate the new zombies DNA, let's add an if statement comparing the CAC 256 hashes of species and the string kitty. So if just gonna copy this here. After I calculate the zombies DNA, which is the stuff that was already here. Let's add an if statement comparing hashes of species and the string kitty. We can't directly pass string CAC 256. Instead, we will pass abi.encode packet as an argument on the left side and abi.encode packet as an argument on the right side. Inside the if statement, we want to replace the last 2 digits of DNA with 99. So it's gonna come here. One way to do this is using the logic new DNA equals new DNA minus DNA remainder by 100 plus 99. Also, you just, I think is the same logic that I used on some of the challenges on Cold War for C++. Because you're getting the remainder divided by 100, you're just shifting the number to the left. To the right, actually. The nearest is 5. Lastly, we need to change the function call inside video on kitty. So I guess this one. Which calls video and multiply and add kitty as last parameter. So video multiply is wrong apparently. Yeah, because I don't have any kitty there. We need to change the function call inside video on kitty when it calls. So maybe it's kitty DNA. Oh, but I'm already passing this here. Maybe it's a string. Oh yeah, it's probably a string. Because I'm comparing the string with the species. So now it's probably somewhere where I put semicolons and I shouldn't. Or I forgot to put them. Maybe here. Yeah, there we go. So after the if statement, you don't put semicolons. Wrapping it up, that's it. If you completed lesson 2, you can check out the demo to the right to see it in action. Go ahead, I know you can't wait until the bottom of this page. Click Kitty to attack, JavaScript implementation, once you're ready to deploy. Contract, as access, blah blah. Let's look at an example of interacting with our deploy contract using JavaScript and Web3.js. So, as the contract, I think is very similar to the previous one. I think they showed this already. Where it's doing the API call here. Now here is the call, the click function, click event listener. Give it a try. So I think I'm just gonna pass this. I completed lesson 2 of CryptoZombies. Unlock. And blah blah blah. Proceed to next lesson. Immutability of contracts. Up until now, Solidity has looked quite similar to other languages like JavaScript, but there are a number of ways that Ethereum dApps are actually quite different from normal applications. To start with, after you deploy a contract to Ethereum, it's immutable, which means that it can never be modified or updated again. The initial code you deploy to a contract is there to stay permanently on the blockchain. This is one reason security is such a huge concern in Solidity. There's a flaw in your contract code, there's no way for you to patch it later. You'll have to tell your users to start using a different smart contract address that has the fix. Yeah, this is a huge issue, actually. But I think people already come up with some solutions, maybe. I'm not really sure, but this is also a feature of smart contracts. The code is law. If you read the code of a smart contract and verify it, you can be sure that every time you call a function is going to do exactly what the code says it will do. Don't later change that function and give you unexpected results. External dependencies. In lesson 2, we hard-coded the CryptoKitties contract address into our dApp. But what would happen if the CryptoKitties contract had a bug and someone destroyed all the kitties? It's unlikely, but if this happened, it would render our dApp completely useless. Our dApp would point to a hard-coded address that no longer returns any kitties. Our zombies would be unable to feed on kitties and would be unable to modify our contract to fix it. For this reason, it often makes sense to have functions that will allow you to update key portions of the dApp. For example, instead of hard coding the CryptoKitties contract address into our dApp, we should probably have a setKitty contract address function that lets us change this address in the future in case something happens to the CryptoKitties contract. Put it to the test. Let's update our code from lesson 2 to be able to change the CryptoKitties contract address. So let me read this again here. Should probably have a setKitty contract address function that lets us change this address in the future in case something happens to the CryptoKitties. But doesn't that conflict with the whole idea that you can't change the code later? I guess it's gonna do some if statements to check if the contract exists and put some fallbacks. Let's update our code from lesson 2 to be able to change the CryptoKitties contract address. Change this to just a declaration. So I need to remove this one and remove this. Delete the line of code, change the line where we create a kitty to just declare a variable. Don't set it equal to anything. Create a function called function. It will take one argument. Public, probably. And it should be an external function. Okay, external. Inside the function, add one line of code that sets kitty contract equal to. So it has to be views here. I think it's view only, not view. Don't remember really well. So inside the function, add one line of code that sets kitty contract I think it should be view, but I'm not sure. Go to Kitty, interface, address. If you notice a security hole with this function, don't worry, we'll fix it in the next chapter. So what's the security hole? Yeah, I'm not sure. So maybe, yeah. So don't need to put view there. Did you spot the security hole in the previous chapter? Is external, so anyone can call it. That means anyone who called the function could change the address of the CryptoKitties contract. I thought the external was just for the functions that inherited. Maybe I'm probably confusing the names. I forgot which one is for contracts that inherit. Oh, but maybe you can create another contract and inherit this one, even though you didn't make it. That's the thing. That means anyone who called the function could change the address and break up our dApp. We do want the ability to update the address in our contract, but we don't want everyone to be able to update it. To handle cases like this, one common practice that has emerged is to make contracts ownable, meaning they have an owner who has special privileges. Yes, I guess that's what's happening. External allows for for contracts that inherit the other contract to access the function, but you don't need to be the way that it was before. You don't need to be the owner, so anyone can create another contract that inherits the function from this one after it is in the blockchain. Below is the Honourable Contract taken from the Open Zeppelin Solidity library. Open Zeppelin is a library of secure, community-vetted smart contracts that you can use in your own dApps. After this lesson, we highly recommend you check out their site to further your learning. Give the contract below a read through. You're going to see a few things we haven't learned yet, but don't worry, we'll talk about them afterward. So ownable, so address private owner, event ownership transferred. The ownable constructor sets the original owner of the contract to the sender account. Return the address of the owner. So if called by any account other than the owner. Yeah, so this is the decorator stuff where the functions are going to be replaced by this underscore here whenever you use the modifier. Return true if message sender is the owner of the contract. Allows the current owner to relinquish control of the contract. Announcing true ownership will leave the contract without an owner. It will not be possible to call the functions with the only owner modifier anymore. So owner address 0 allows the current owner to transfer control of the contract to a new owner. So I guess this is in case if you build an application and you want to sell it or change the owner, you can use this function here. Can do things this way. Or maybe if you're creating a token or something, you can renounce ownership after you create it, so nobody has access anymore to the external functions. Transfers control of the contract to a new owner. New owner, the address to transfer ownership to. A few new things here I haven't seen before. Constructors. Constructor is a constructor which is an optional special function that has the same name. Okay. Modifiers. So where is the modifier used here? Oh, yeah, here. Only owner is using this one. So this requires it replaces whatever is inside of this function with here. And so it adds this extra functionality to the function. It's the same way that the decorator works in Python, I think. So the Honourable Contract basically does the following. When a contract is created, its constructor sets the owner to message sender, the person who deployed it. It adds an only owner modifier, which can restrict access to certain functions to only the owner. Allows you to transfer the contract to a new owner. Only owner is such a common requirement for contracts that most Solidity dApps start with a copy-paste of the Honourable Contract, and then their first contract inherits from it. Since we want to limit set key contract address to only owner, we're going to do the same for our contract. To limit, okay, only put it to the task. We've gone ahead and copy the code of the Honourable Contract into a new file. Honourable.sol. Let's go ahead and make zombie factory inherit from it. So I need to import and same directory, probably Honourable.sol. Yeah, how does this import works? It's still not clear to me. Because if we're deploying things that depend on other contracts, there isn't a way to know in the blockchain, I think, what the folder structure is. Maybe just I don't have to put this. I'm not sure. But then you could have conflict of interest between a conflict of interest, a conflict of names from other contracts that were done. So I don't understand this really well. I'm gonna ahead and copy the code of the Honourable Contract into a new file. Let's go ahead, modify our code to import the contents of Honourable.sol. To do this, take a look at zombie feeding.sol. Yeah, you have to specify the directory. Maybe I'll look this up later. If you don't, okay. Modify the zombie factory contract so it inherits from Honourable. So is Honourable. And yes, is this function, this contract here, which is the one that comes from the explanation, probably. Again, you can take it if you don't remember how it's done. Okay. So I forgot the semicolon, probably. Yeah, there we go. Now that our base contract zombie factory inherits from Honourable, we can use the only owner function modifier in zombie fitting as well. Modify this function. So it's probably, I think it comes after this. Only owner. I don't remember. Oh, it comes after. So external It's also honorable. A function modifier looks just like a function but it uses the keyword modifier instead of the keyword function, and it can't be called directly like a function can. Instead, we can attach the modifier's name at the end of the function definition to change that function's behavior. Notice the only owner modifier on the renounce ownership function. When you call renounce ownership, the code inside only owner executes first, then when it hits the thing statement, only goes back. While there are others where you can use modifiers, one of the most common use cases is to add a quick require check before a function executes. In the case of only owner, adding this modifier to a function makes it so only the owner of the contract if you deploy it, can call that function. Note, giving the owner special powers over the contract like this is often necessary, but it could also be used maliciously. For example, the owner could add a backdoor function that would allow him to transfer anyone's zombies to himself. So it's important to remember that just because a dApp is on Ethereum does not automatically mean it's decentralized. You have to actually read the full source code to make sure it's free of special controls by the owner that you need to potentially worry about. There's a careful balance as a developer between maintaining control over the app such that you can fix potential bugs and building an ownerless platform that your users can trust to secure their data. Yeah. So put it to the test, add the only owner, so I think that's correct. And I think it's impossible to make something fully decentralized because decentralization depends on centralization. Just the same thing is an object in space time. So it doesn't make sense to think about things as purely decentralized or purely centralized. Anything that exists is going to be a combination of both. And it's about trying to strike the best balance of both possible so the technology doesn't destroy itself over time. Great, now we know how to update key portions of the dApp while preventing other users from messing with our contracts. Let's look at another way Solidity is quite different from other programming languages. Gas, the fuel Ethereum dApps run on. In Solidity, your users have to pay every time they execute a function on your dApp using a currency called gas. Users buy gas with Ether, the currency on Ethereum. So your users have to spend Ethereum in order to execute functions on your dApp. How much gas is required to execute a function depends on how complex the function's logic is. Each individual operation has a gas cost based roughly on how much computing resources will be required to perform that operation. Adding to storage is much more expensive than adding two integers. Total gas cost of your function is the sum of the gas costs of all its individual operations. Because running functions costs real money for your users, code optimization is much more important in Ethereum than in other programming languages. If your code is sloppy, your users are going to have to pay a premium to execute your functions. And this could add up to millions of dollars in unnecessary fees across thousands of users. Why is gas necessary? Ethereum is like a big, slow, but extremely secure computer. When you execute a function, every single node on the network needs to run that same function to verify its output. Thousands of nodes verifying every function execution is what makes Ethereum decentralized, and its data immutable and censorship resistant. Yeah, I don't know about that, but one thing I was thinking about is, and I know from the Nasdaq Librem it's probably extremely difficult for people to coordinate and everyone to block the blockchain and stop people from having easy access to it. But how is it possible to have access without any external influence? For example, how do you buy how was the first Bitcoin purchased? I don't understand really well how that works. I guess, yeah, the beginning is probably not worth anything, and then some people pass around, and then people start agreeing that to change one abstract thing into another abstract thing. So money through Bitcoin. And the only thing that matters is the trust that the thing is worth anything. Not in the case of Ethereum, but when it's just money. But it's still very weird to think about. I guess if everyone started using crypto instead, not Bitcoin, but some like USDC or something like that, then it would be technically almost impossible to censor. Because you can't really prevent access from it. As long as you have a bunch of people around the world running nodes. So I guess the question I have is how to access the blockchain without any intermediate stuff. Because so far I've only used exchanges to pass, even if you have a private wallet, you still need to pass through an exchange to get money into the wallet. Yeah, that's the thing that I was thinking about. How do you get crypto without any exchange? I guess you need to rely on knowing other people, probably. And you can use decentralized exchanges, but how do you put the money on the decentralized exchange in the first place? That's the thing. You always need to pass through something until you get through it. Then once you get through it, then you can do anything from there. But that bridge is not clear to me. I think it's always going to be connected to the, let's say, outside. And so it's very hard to censor, but not impossible. Unless everything moves through it, so we don't need anymore to have that bridge because everything is already inside. If that makes sense. The creators of Ethereum wanted to make sure someone couldn't clog up the network with an infinite loop or hog all the network resources with really intensive computations. So they made it so transactions aren't free, and users have to pay for computation time as well as storage. Note this isn't necessarily true for other blockchain, like the ones the CryptoZombies author are building at Loom Network. It probably won't ever make sense to run a game like World of Warcraft directly on the Ethereum mainnet. The gas costs would be prohibitively expensive, but it could run on a blockchain with a different consensus algorithm. We'll talk more about what types of dApps you would want to deploy on Loom versus the Ethereum mainnet in a future lesson. Struct packing to save gas. Lesson 1, we mentioned that there are other types of uints, etc. Normally, there are no benefits to using these subtypes because Solidity reserves 256 bits of storage regardless of the uint size. For example, using uint 8 instead of uint won't save you any gas. But there's an exception to this inside structs. If you have multiple uints inside a struct using a smaller size uint, when possible, we will allow Solidity to pack these variables together to take up less storage. So for example, this. For this reason, inside a struct, you want to choose the smallest integer subtypes you can get away with. You also want to cluster identical data types together, i.e. put them next to each other in the struct, so that Solidity can minimize the required storage space. For example, a struct with fields UNC A, B will cost less gas than a struct with fields A, C, B, because the UN32 fields are clustered together. Interesting. Put it to the test. In this lesson, we're going to add 2 new features to our zombies, level and read time. The latter will be used to implement a cooldown timer to limit how often a zombie can feed. So let's jump back to Zombie Factory. So, add 2 more properties to our zombie struct level. A uint32 level and read time uint. Oh, it's not. Come on. "32 bits is more than enough to hold the zombie's level and timestamp, so this will save us some gas by packing the data more tightly." Okay. Chapter 5, Time Units. The level property is pretty self-explanatory. Later on, when we create a battle system, zombies who win more battles will level up over time and get access to more abilities. The red time property requires a bit more explanation. The goal is to add a cooldown period and amount of time a zombie has to wait after feeding or attacking before it's allowed to feed attack again. Time units. Solidity provides some native units for dealing with time. And now we return the current Unix timestamp of the latest block. The number of seconds that have passed since January. Okay. Unix time is traditionally stored in a 32-bit number. This will lead to the year 2038 problem. And 32-bit Unix timestamps will overflow and break a lot of legacy systems. Damn, I didn't know that. So if we wanted our DApp to keep running 20 years from now, we could use a 64-bit number instead. But our users would have to spend more gas to use our DApp in the meantime. Design decisions. And that's very interesting. I wonder which one the blockchains decided to use. Probably the 64. I would imagine. But they did this a long time ago, so not sure. And I think date, times, operations are part of the source code of the blockchain itself. So I assume they probably use 64-bit. But it's an interesting thing to think about, because if they didn't, then that would mean that they would break the whole thing, probably, based on this. Solidity also contains the time units: seconds, minutes, hours, days, weeks, and years. This will convert to a unit of the number of seconds in the length of time. So 1 minute is 60, 1 hour is 3060, 3600, 86,000, etc. Here's an example of how these time units can be useful. So let's update you now. We return true if 5 minutes have passed since update timestamp was called. False if 5 minutes have not passed. Okay, we can use these time units for our zombie cooldown feature. Put it to the test. Let's add cooldown time to our DApp and make it so zombies have to wait 1 day after attacking or feeding to attack again. declare a uint called cooldown time. Now I'm not sure if I should use 1 days or just days. Probably 1 days. Free the program. If you set it equal to 1 day, it won't compile. Okay, so it has to be 1 days. Since we added a level and ready time to our zombie struct in the previous chapter, we need to update create zombie. So I have to update this. Choose the correct number of fragments when we create a new zombie struct. So name, DNA. I don't understand. So this. Yeah, I'm not sure now what I should do. Choose the correct number of fragments. Update the zombies push line of code thread, 2 more arguments, 1 for level. Also, I need to put here probably. Oh, at the end, actually. But then I have to put it past them as arguments as well. Okay, so cooldown time is here. I'm not sure if I should put uint 32 or not. And then level, I'm not sure if I should put in the arguments of the function. If I do, I would have to change the other one here. Yeah, it's probably it doesn't feel right. So I'm probably missing something. Int 32 is necessary because now returns a uint 356 by default, so we need to explicitly convert it to a uint 32. So guys, this part is correct, but the level I don't understand. We will equal the current Unix timestamp in seconds plus the number of seconds in 1 day, which will equal the Unix timestamp 1 day from now. Later, we can compare to see if this zombie's ready time is greater than now, to see if enough time has passed. Choose the zombie again. We implement functionality to limit actions based on ready time in the next chapter. So it has a problem here. We need to cool down 1 days. Maybe I have to put equal. And then here, the level thing. Let's see if I put uint level. Yeah, I knew this didn't sound like it was correct. So I don't understand. What do I have to put here? Because it wasn't saying to change the parameters. Let's try just uint, it's probably not gonna work. What if I leave it like this? It's probably not gonna work, so. Let me see if I just erase them. That doesn't work. Since we added a level in runtime show zombie, the create zombie choose the correct number of fragments. Push line of true codes. True. Oh, update. No, the zombie push. One for level. And did I try to? Yeah, I think I tried to put just level here. It did not work. Yeah, it doesn't make sense to me. This is just about the time. I think I'm just gonna look at the solution for this one. Oh, I need to put the number. It doesn't make sense to me because it's gonna change each time you push. So I don't know. Now that we have a ready time property on our zombie struct, let's jump to zombie feeding.so. Implement a cooldown timer. We're going to modify our feeding multiplier such that feeding triggers a zombies cooldown, and zombies can't feed on kitties until their cooldown period has passed. This will make it so zombies can't just feed on unlimited kitties and multiply all day. In the future, when we add battle functionality, we'll make it so attacking other zombies also relies on the cooldown. First, we're going to define some helper functions that let us set and check a zombie's ready time. Passing structs as arguments. You can pass a storage pointer to a struct as an argument through a private or internal function. This is useful, for example, for passing around our zombie structs between functions. So it's passing the struct as an argument here. This way you can pass a reference to our zombie into a function instead of passing in a zombie ID and looking it up. We should start by defining a trigger cooldown function. Oh, accidentally pressed the mouse stuff. So function trigger cooldown to take one argument a zombie storage pointer. So zombie storage. So this one has to be view, I think. Internal. Yeah, it didn't mention anything, so I'm not gonna put it, but maybe it doesn't because it's just a reference to the thing. Zombie storage. Zombie. The function body should set zombie.readyTime to uint32. Yeah, so readyTime is the property of the zombie. So don't need to declare, I think. I always forget to change the auto. So next, create a function called isReady. IsReady. This function will also take a zombie storage argument named zombie. Zombie storage, zombie. It will be an internal view function. Also, this one is internal view. I still don't get it really well when to use view or not, or pure. Or it turns a boom. Because here you are modifying the ready time property of the zombie. So why isn't view required here? The function body should return zombie ready time, which will evaluate. So I guess it's just return zombie dot ready time. No. This function will tell us if enough time has passed. Yeah. I think I'm gonna stop here. And then if I still have some time, I'm finishing a website off stream. And I don't think I'm gonna finish today because it's probably gonna take several hours. So if I get tired of doing that, I'm probably gonna come back and continue to do this today. If not, I'll come back another time and continue. So see you.